So thank you very much for coming. This is our third attempt to have a in-person mirror symmetry conference, the trademark of IMSA. And finally, we can have that in a hybrid version. So it's a great pleasure that you are all here, and we can continue in the usual modus operandi in person, almost. And it's a great pleasure to introduce Maxim Kontsevich from IHS, who is going to tell us about non-holomorphic deformations of Landau-Ginzburg model. Max?
Okay, thank you very much. And really from IHS now. So sorry for not having in person. So my first two talks will be on the subject, and third talk will be on another. So let me start. So I will start with kind of model story, what we want to kind of imitate. It's a pretty old story starting from Milner, Arnold, Tom. It's about universal unfolding of isolated singularities. So suppose we have a germ of analytic functions in several n variables and complex variables. So abstractly, we have some n-dimensional complex manifold point and germ function here, and assume that it's a critical point. So derivative vanishes here, and it's isolated for all point nearby. The derivative is not zero. So what one can say that it's what one can rephrase it in other ways, that if consider level set of my function passing through this critical point, then I get a hypersurface which is smooth except one point, which will be isolated singularity of y0. So I can see it's either isolated critical points or isolated singularity of hypersurface. Yeah, so the fact that this critical point is isolated is equivalent to the fact that this algebra of functions on the locus of critical points in the neighborhood of this point is finite dimensional. So you get kind of like seed point. And this algebra of functions on the critical locus, consider germs of function on the critical locus, it's given by equations that all derivatives of my function vanish. So it's quotient of the ring of germs of analytic functions modulo the ideal generated by derivatives. So the main characteristic of isolated singularity is what's called Milnor number. It's numbers could be 1, 2, so on. And it has several equivalent definitions. First definition is the dimension of the local algebra, is portion by the ideal. The second definition is it's a topological definition. One can see the cotangent bundle to a manifold. Then it has two Lagrangian submanifold, zero section, and the graph of differential. And this isolated singularity means that the intersection point y0, 0, the 0 is direction cotangent, coordinate in the cotangent direction, is isolated intersection point. And so we get two closed smooth submanifolds which intersect locally at one point, and with this well-defined local intersection number, we just shift a little bit and we see how many non-trivial intersection, kind of generic intersection points we have. Or the third definition, it's more or less reformulation of this. It's you consider generic small deformation of a function depending on some parameters, and then the function will have several holomorphic Morse singularity near this point, and this number of this Morse singularity is a Milnor number. So if Milnor number is 1, if and only if the singularity is holomorphic Morse singularities. Milnor number of 2, it's kind of like z1 cube plus quadratic form in other variables. Yeah, so it was whole activity in 60s and 70s to classify singularities according to Milnor number. For small Milnor numbers, we can do it. So what are basic examples of calculation of Milnor number? If you get function in one variable z to power k, and k should be at least 2 to have single point, then the Milnor number is k minus 1, because the derivative is z to power k minus 1 up to constant, and you get units on dimensional quotient. Or you deform a little bit, you get k minus 1 critical points of generic polynomial of degree k. And if you consider this next simple example. So you get several variables and consider sum of powers of variables, then to the product of Milnor numbers for corresponding variables. So in general, there's a notion of it's called Thom-Sebastiani sum. You have function on one variety, function on another variety, then you get sum of pullbacks on the product of two varieties, and the Milnor number will be product of Milnor numbers. Okay. Yeah, so you get the main characteristic is the Milnor number, and if it's small enough, then you essentially get a unique singularity of such Milnor number. Now I want to define you something called universal unfolding. Now one can say it's kind of deformed singularity with sufficiently many parameters, but let me give you some kind of canonical definition, which is not in the textbook. First, you choose an open Stein neighborhood of your point with a strictly holomorphic boundary, holomorphically convex boundary. So Levy form will be strictly positive. For example, in local coordinates, you consider just small ball, small round ball, and you get this neighborhood. And I assume it's small enough, so yeah, so since my function, my germ is actually actual function on this neighborhood, and it's only one critical point. It's my point y0, so don't make it too big. Yeah, so I get a function on the ball having one critical point y0 inside. Now consider infinite dimensional complex manifold of all various functions in this domain. Namely, a defined f0 of the closure of my domain will be functions which are holomorphic on some neighborhood of the closure, so it's still larger neighborhood, and such that on the boundary functions have no critical points. My original function it belongs to this submanifold, obviously, because the only critical points is strictly inside. Yeah, so I get some infinite dimensional complex manifold. In what sense you ask? It's, for example, it's obvious what as a factor of finite dimensional complex manifold. We can consider about finite dimensional holomorphic families of such functions. And this condition is open. So you get some big open domain in some infinite dimensional guy. And it has infinitely many components. In fact, I have no idea how many of them. But one of obvious topological invariants, it's what one can call global Milnor number. You consider graph of differential of my function g and zero section in cotangent bundle. Again, they intersect in some finitely many points because it should be analytic subset contained strictly on, it should be compact and contained in open ball, should be only zero dimensional. And you consider intersection number in topological sense. And this intersection number doesn't change under continuous deformation of function g because the critical points never touch the boundary. Yeah, so we get this infinite dimensional manifold, and we define a subbundle of the tangent bundle. The tangent space to this guy at any point is the space of all functions on u defined in the neighborhood of u bar. In fact, if you have any function in this f0, and you have any other function, you can multiply the second function by constant and add to the first one, and still don't have critical values on the boundary because the boundary is compact and you get some uniform bound. So it's really open domain in some obvious sense, and the tangent space is the whole space of functions. And this whole space of functions contain a vector subspace, namely apply all holomorphic vector fields defined in u bar in its neighborhood to my function g, to begin holomorphic function in the neighborhood of u bar, it's subspace. And it's very easy to see that it has finite codimension, and the codimension is equal to this global Milnor number, which is invariant of the connected component. And what you get is a foliation. It's formally satisfies Frobenius criteria. Any two vector fields on this infinite dimensional guy tangent to foliations if you make commutator, it's again tangent to the foliation, to this distribution. So it's a foliation of finite codimension. And even this situation is infinite dimensions, it's pretty obvious that one can define locally for each point a germ of space of leaves, which will be germ of finite dimensional manifold. So this universal unfolding is a germ of space of leaf affiliations at point represented by our functions. So it's canonically associated with F, germ of finite dimensional manifold. It has dimension equal to this Milnor number, and the dimension and this germ doesn't depend on the choice of this auxiliary open neighborhood. If you stick one to another, you get identification of these germs. Yeah, it's kind of geometric definition of this universal unfolding. And again, the simplest example, we get function z to power k. Then the universal unfolding consists of adding terms of degree k minus 2 and up to 0. So the k minus 1 parameters. So that the universal unfolding will be germ of 0 in coordinate k minus 1 dimensional space is coordinate c0 up to ck minus 2. Okay, so there's this universal unfolding, and so it's some germ. One can say several things about it. First, this guy, it depends only on finite jet of function of at y0, because kind of very simple result, but that by a local change of coordinates, maybe it's trivial linear part, one can vary arbitrarily sufficiently high Taylor coefficients of that. So it means that it defines not, you don't really need to know the whole series of F and convergent series, you need to know only a few terms. And that means that one can define analytic germ, this analytic germ, if you know only not convergent series, but formal germ of function with isolated singularity. So it's a bit paradoxical. So we can have, for formal germ, one can say what is isolated singularity in this sense this local algebra is finite dimensional. And again, you can truncate, it depends on only first few Taylor coefficients, and we set, let's say, all high Taylor coefficients are 0, so you can replace it by polynomial, and then the geometric construction arises. Okay, so that is analytic germ associated to formal isolated singularities, and the next thing is a group of automorphisms of a germ, of even a formal germ, acts on this universal unfolding to give some finite quotient, as a group of connected components. And here it's convenient to think about of formal power series, not convergent one, because for four power series, a group of automorphisms is a pro-algebraic group. It's you consider how text of Taylor coefficients up to a certain order, get finite dimensional group, and you get projective limit. In this pro-algebraic group, if one follows the description, the Lie algebra of this group acts on moduli space trivially. And the group of connected components is finite, because it's moves to some, after some steps, this is to the unipotent extensions. So you get by zero of some a finite algebraic group of finite dimension. So get the finite, so the group acts through finite quotient. This finite quotient you can see on the actions just on the tangent space at base point on your original manifold. Yeah, so this germ also doesn't change if you consider Storm-Sebastiani sum of your function with more singularity. You get as a variables n plus first variable squared. It will be the same germ. Yeah, so there's a kind of natural equivalence relations called stabilization. You add to function more singularity, you don't distinguish them. What else? Yeah, if you consider tangent space to any point on this germ, you consider function close to f, defined in some domain u bar. Then the tangent space is a quotient by this space of functions modular the subspace obtained by application of vector fields, and it's ideal. So, and what you get is actually algebra functions, the critical locus of deformed functions. So it's commutative associative finite dimensional commutative associative unital algebra. So every point is commutative associative unital algebra. It's a main feature. And so the next one is you get an algebra, countable dimensional algebra, polynomial vector fields and non-variable acting on this guy. Namely, for vector field Tn dut in this the algebra of vector field, the associative operator. So the speed of vector field at any point g close to f will be g to power n. And if you look at the definition, it's actually nth power in tensor in the sense of this associative product on the tensor space of Euler field which corresponds to n equal to 1 in a scalar function. Yeah, and then the final kind of beauty of this moduli space, if you deform the function a little bit and you get several critical points instead of one, and you get local germs of these critical points f1 and r, then this moduli space of universal form of f near this deformed point is canonically identified with moduli space of f1 times moduli space of 2 up to moduli space of r. It canonically splits the product of the same space associated with a smaller Milnor number. And we have a conservation law. Milnor number of the whole function is sum of Milnor numbers of new singularities. Yeah, so it's a really lovely object. And one can try to make from this some universal variety. Like for any integer m, you consider positive integer m, consider moduli stack of stable classes of formal isolated germ with Milnor number m. And such that critical value is 0. This is very important constraint. This is some finite dimensional gadget because it depends only on finite dimensional coefficients. And it's actually a stack. It's not a variety because you have stabilizers, and stabilizers are finite group. This thing could be very complicated for large M. It's some algebraic dilemma of stack of finite type. And it is defined over rational numbers because one can consider form power series over any field of characteristic 0. But when we consider this at least formal thickening, for each point you get maybe formal completion of this MF, they glue together, and what we see get kind of smooth dilemma of a stack of kind of orbifold of dimension m, which contains as a closed subset this moduli stack mm0. And this formal thickening, it's also defined over rational numbers, but in general it's not algebraizable. So this not a completion inside some ambient algebraic variety. And there's also kind of funny feature. We have not only formal germs from this constructor, but analytic germs. It's also extends to complex analytic orbifold germ. And then we can speak about functions which are kind of like form power series with rational coefficients and still convergent. So it's kind of mixture between formal and analytic geometry. Yeah, so it's pretty tricky object, and it's not algebraic, but close to algebraic geometry. And for a larger M becomes more and more complicated. It's still smooth, but more and more complicated. And eventually, I think it's kind of like universal moduli space of everything. It will be not. It's like moduli space of all varieties. Eventually, it's too complicated. Yeah. Now, what about next stories? For as a series, I want to speak about spectra and certain semi-continuity. So the first, there is a old result by Saiter that a germ of isolated singularity is a fixed point of the earlier vector field if and only if the singularity is quasi-homogeneous. So one can introduce locally some coordinates and endow them with certain positive weights, which are rational numbers, such that my function f has weights +1, so it will be actually quasi-homogeneous polynomial. And then if singularity is quasi-homogeneous, then the local ring is automatically graded by rational numbers, non-negative rational numbers. And I define the spectrum of singularity as a collection of several rational numbers with multiplicities. This collection consists of mu f numbers. So Milnor number will be number of elements in this collection. And the weights will be and the numbers which are the following. You can see the graded basis of this local ring, and shift by non-positive numbers. Some over this weights lambda I minus 1/2, and it will be non-positive numbers. Again, in this simplest example, which you start with, the function z to power k, you get numbers between -1/2 and +1/2. They're equally spaced, so it's arithmetic progression step 1 over k. Why this sheaf is convenient? So in original papers, people didn't do this sheaf. First, the spectrum is preserved by stabilization. If we add the square of extra variables, it will be the same number. Then it's symmetric, the center of symmetry is 0, and it's compatible with Thom-Sebastiani sum. So consider two functions of two different groups of variables, take the external sum, you get sum of spectra. Then Chotov-Spiarini work of Barchenko in special case, and that's Steinweg in general case. They extended the definition of spectra to non-quasi-homogeneous isolated singularities, and the definition is pretty tricky. It's used mixed-Hodge structure and homological of vanishing cycles, so in tomorrow lecture I will return to it, and prove semi-continuity result, which was originally conjectured by Arnold. So if you have germ with isolated critical point, and split in the so it's one point and split in a collection of germs, one of R, then each new germ is kind of simpler than, of course, it's a small Milnor number, but also it's kind of more narrow, and but in the simple sense, it's you consider a number of elements in the spectrum of any semi-closed interval of length 1, it will decrease. Yeah, in original argument, you have semi-open interval closed on the left, but because of symmetry of spectra, it's the same as closed on the right. Okay. Yeah, so that's our model story, and now how we want to generalize it. So we generalize to the situation and get a holomorphic function f, maybe it's not isolated singularity, so critical locus is something, but instead of isolated, I said it's compact. So it generalizes the case of isolated singularity because then it's isolated to get a point which is compact. Yeah, if you have such a situation, one can define the following differential graded Lie algebra. It will be graded both in positive and negative degrees, and components in degree k is the following thing. You consider kind of Dalbo resolution of polyvector fields. So it will be a section of I6 to the power of vector fields in holomorphic direction and J6 to the power of one forms in anti-holomorphic direction. And we put this grading G minus A is equal to K minus 1. So this Lie bracket on this gadget will be Scott and Inhouse bracket for polyvector fields and cup product for d-bar forms. And the differential is given by combination. It will be d-bar differential and Schotten bracket with the function. Yeah, so you get this DG Lie algebra, but up to quasi-isomorphism depends on the germ of pair near at the critical locus. So you can shrink your Y to arbitrary small neighborhood of critical locus. And the things which I kind of formulate as fact, but it's actually a conjecture in the abstract of my talk, is an abstractness conjecture. If there exists a Kahler metric and a holomorphic volume element on Y just near critical locus, not the whole Y in a small neighborhood surface, then then this differential grade Lie algebra is formal, or at least kind of like homotopically abelian. or it means that derived moduli space is a formal germ of smooth finite-dimensional supermanifold. The cohomology of this algebra are always finite-dimensional. Yeah, so that's basic conjecture, and I will discuss this conjecture. So first, this picture contains a case of isolated singularities. If you have isolated singularities, then in the neighborhood of any point, one can always find a Kahler metric. Just introduce any coordinate, choose Kahler metric, and non-vanishing holomorphic volume form. Again, introduce any coordinates and constant volume form. So it's absolutely for free. And in this case, this formality is absolutely clear because if you consider this DGL algebra, in case of isolated singularity, it has non-trivial cohomology only in degree +1. Just recall this, you have differential here, d bar and commutator with f. You just do a little spectral sequence, you consider cohomology coefficients in d bar, and because its small neighborhood is Stein, it's you have only kernel, you have only holomorphic sections. So that's Lie subalgebra considered germs of holomorphic vector fields. Now d bar will vanish here, and then consider commutator with f. It will give you essentially a causal complex which has cohomology only 1 degree, and it will be degree +1. So this cohomology of algebra concentrated in degree +1, and it's actually this local ring shift placed in degree +1, and there is really no room for high commutators in infinity structures. So it's automatically formal in moduli spaces. Smooth actual manifold, not super manifold. Yeah, there is another case when this unabstractness is clear, namely when my function is 0, identically 0. By assumption that critical locus is compact, it means that my variety is compact. So we speak about compact Calabi-Yau varieties, and there is a generalized Young order of unabstractedness. Yeah, and here the story is the following. If we assume the unabstractness, we can obtain a formal germ of supermanifold. Deformation theory works only in these formal settings, and it carries the same geometric structures as the universal form of isolated singularity. So the tangent space is a commutative associative unit of algebra, finite-dimensional one, superalgebra. There is a canonical Euler vector fields whose powers with respect to this product generate DT algebra, linear vector fields in one variable, and then you get also product decomposition. If you get any point close to the origin, and here too, because it's formal, I think we should speak maybe points over some non-convenient field. Then the neighborhood of this point split canonically in the product of small supermanifold labeled by finite set, which is the set theoretic spectrum of multiplication of this Euler field acting on the tangent bundle. Yeah, so deformation theory it gives only formal manifold, and as I discussed, in case of isolated singularity, we get actually germs, and this open question: can we define naturally analytic germ in such situation? It's about the formal one. Yeah, actually, this situation when I get product Euler field and splitting locally in product of smaller varieties appears in different contexts. So the first one is you can see the theory of Gromov-Witten invariants. You start with a compact symplectic manifold, infinity manifold. It has some genus 0 Gromov-Witten invariants, and it gives structure of is the known Frobenius manifold in the open domain and homology with coefficients in some local field. Then we use local field in order to ensure eddy convergence of infinite series. So the product of tangent bundle is the usual quantum product, and Euler field come from the grading axiom. There is a kind of plural, it's a geometric origin or symplectic origin, and this algebraic origin You start from a smooth and proper Z-mod 2 graded Calabi infinity category with degenerated spectral sequence Hodge to germ. And then the derived moduli space of such categories controlled by cohomological complex is automatically smooth. The product on tangent space is a cup product on Hodge cohomology, and the Euler field is given by simultaneous infinitesimal scaling of all high products with the same speed. Yeah, in fact, this second construction, now maybe zero construction, it's what Landau-Ginzburg model which I talked before, that variety in the function. This second construction is heuristically the most general one. It contains, in a sense, the first construction when you think about Fukaya category of your variety, and for the Landau-Ginzburg model, you consider category of matrix factorizations, or it's equivalent, you consider DB sync of this hypersurface, which is singular locus of my function. Yeah, here I should assume that the critical value is 0 if we speak about matrix factorizations. Yeah, so this number 2, it's kind of most general example, but one should be a bit careful because one can imagine that these Fukaya categories are not really smooth and proper categories, and, like mirror dual to some non-algebraic varieties. So it's not, in principle, it's not clear what is the most general source of such geometric structures. Yeah, and we have an ongoing project with D.Auroux, Tony Painter, and Tony Liu for the potential application of Gromov-Witten invariants to birational geometry. And here one needs to understand splitting of eigenvalues of the Euler field at generic points of certain submanifold of Frobenius manifold. Namely, in the special case, when my variety is symmetric manifold set to a smooth complex projective variety, so it's algebraic one. So one have a pure even subspace in cohomology spanned by classes of algebraic cycles. This depends on field of definition. You can also ask arithmetic questions. But anyhow, the space of algebraic classes contains in subspace of classes represented by PP forms in even cohomology group. So it's some part of diagonal part of Hodge diamond. And under mirror symmetry, for example, effect is fun, and imagine this mirror dual Landau-Ginzburg model. This direction, this part of Frobenius manifold we deform only along HPP cycles correspond to the following things. In derived moduli space of now ODG algebra such as varieties in the function, I consider solution of Markov equations in degree 0, in degree 1, and in my algebra, so it will be degree 0 of the derived moduli space, and mod out by up to H equivalent given by J0 action. Yeah, and yeah, so that's really kind of nice correspondence between Hodge classes and this grading which I introduced on my algebra. And then consider deformation corresponding only in this having components only for I equals 0 and 1. Then you see deform function, deform Beltrami tensor, deform almost complex structure of this guy. Or somebody is talking. Yeah, so it will be, so it corresponds to holomorphic deformation of the pair for line function, but it corresponds to H00 and H11 of X. But if you deform by H22 of X, it gives some deformation which don't have clear holomorphic interpretation. It will be non-holomorphic object. And actually, will be my goal of my lecture tomorrow to give some geometric understanding of such deformations. Then there's no obvious holomorphic complex geometry, and how to do A model, B model, and extend serial spectra and semi-continuity. Yeah, now I turn to the question how to prove the unabstractedness. Yeah, so I recall that for abstractness we use a volume element and Kahler form. So first choose a volume element. The volume element gives you identification of zero power of tangent bundle with zero power of cotangent bundle. And also the volume element gives a natural structure of differential graded Battalion-Minkowski algebra of this algebra. This Battalion-Minkowski operator is given by divergence with respect to this volume element. Yeah, so it's a long time ago with Neil and Tony wrote a paper Hodge-theoretic aspects of mirror symmetry, and we built some general story about this Battalion-Minkowski algebras and homological smoothness. And the conclusion that this unabstractness of formality for this original D algebra follows from a purely linear equation, not involved in any commutators, from the degeneration property of some certain spectral sequence, which one can say the following. You consider sheaf of complexes on Y given by form power series and auxiliary variable U is coefficients and forms. Here we use identification of polyvector fields and forms, and this differential is given by small deformation of multiplication by df, u times the RAM differential. And this generation property says that its space is a free finite rank module over series in U. Yeah, the more precise things maybe truncate by some power if you get really finite dimensional algebras and such modules. So this statement, this assertion, which you want to be true, now no longer involves a volume element. You can forget that variety has volume element because it's now use forms instead of polyvector fields. What we really need here is only existence hypothetically only of a Kahler metric. So we have to prove this Frobenius result, and I propose some strategy and propose two conjectures about Witten's deformed Laplacians from late 80s. And these conjectures are very general and quite interesting by itself. And if I analyze the logic, what follows from what, some inequalities, in fact, only the second conjecture is needed for unabstractness. The first one is just for its beauty, but it's not really needed. Yeah. So how to proceed? So what we want to prove? We have now we don't worry about volume element at all. Yeah. So there's no volume element. So we have a non-compact Kahler manifold, and this holomorphic function is a compact critical locus. And we want to prove that this R gamma of this complex of sheaf, for which you can use Delbour resolution, is a free module over series in U. And again, because it's homology supported on the critical locus, you can assume that just keep one component and shift function by constant, so assume the critical value is 0. So what is known, it's again quite a long time ago, Claude Savay and Saito answered the question which I asked them, that if you consider complex, it's kind of a local statement, not global. If you consider complex of sheaf on manifold, don't really need compactness, locus, complex of sheaf of forms is coefficient, and we consider Laurent series, not Taylor series in this guy, and again consider the same default differential. Then complex of sheaf is naturally isomorphic to the sheaf of vanishing cycles, which supported on critical locus after the extension of scalars from rational numbers to Laurent series. Yeah, so kind of we know what this what is homology looks at generic point over U, when we invert U. And so what suffices to prove that this rank of homology at U equal to 0 is the same as a generic point. So the homology of sheaf of vanishing cycles. So the homology at U equals 0, we get G bar plus multiplication by df. What is this? It's it's cohomology of Y with coefficients in the complex of holomorphic vector bundles in Dalbo resolution. You consider forms of all degrees and differentials given multiplication by df. And these complexes are slightly outside of compact subset critical locus. So it's pure, this space cohomology has pure holomorphic origin. The second space, vanishing cycles, also described as in topological ways, cohomology of a pair. Namely, we take a small neighborhood of a critical locus of my function with the same critical locus of a real part of my function, real valued function, which is sufficiently nice boundary, such that if you restrict things on the boundary, it has no critical values close to zero, yeah. So it's a little kind of box around critical locus. And now in the critical locus, you consider two open domains when my real part of my function is less than epsilon and contains the real part of less than minus epsilon. And when epsilon is sufficiently small, the cohomology of this pair stabilizes, and this is equivalent to cohomology with coefficients in this vanishing cycle. Yeah, so we want to prove that these two cohomology groups coming from holomorphic and topological description are the same. Yeah, so we get two different situations. In a complex world, we can forget about origin of the story, a finite complex of holomorphic bundles on some complex scientific manifold, which is acyclic outside of a compact subset. So we get, in kind of speaking more abstractly, we get perfect complex with compact support on the scientific manifold. And in the real world, we get just real valued function, a real part of my holomorphic function on infinity manifold. We forget about complex structure with a compact critical locus. So that two situations produce cohomology group, and you want to prove that cohomology space is isomorphic. Now let us do the following. We introduce two kind of Laplacian depending on small parameter. Small positive parameter. In a complex case, we consider the following guy. We consider d bar plus rescaled by 1 over epsilon multiplication by df, and take anti-commutator with Hermitian conjugate operator. And in the real case, we consider d plus 2 times epsilon inverse differential with real part of my function rescaled with this again conjugate operator. What do I mean by Hermitian conjugate operator? My manifold is not compact, and but there was I introduced some Kahler metric norms and so on. There are formally adjoint operators if you apply it to compactly supported sections, but there's really no global Hilbert space yet. Yeah, so it's you get these two Laplacians. Somebody is asking. Oh, sorry. Yeah, and in the when you get Kahler metric and you get kind of usual Kahler identity and complex Laplace. Oops, maybe 1/2. Yeah, twice complex Laplacian is real Laplacian. So it's misprint. Yeah. So what we talk here about, it's not actual operators in Hilbert space because varieties are not compact, and I didn't say what are boundary conditions. Anyhow, this cohomology of these operators depends only on arbitrary small neighborhood. And what we really can do, it's I don't really know precise definition, but for example, one can consider operators on a small neighborhood with some smooth boundary and put something like Dirichlet boundary condition on the boundary, so that well-defined self-adjoint operators. So use some kind of like reflection with respect to boundary. Yeah, so one should deal somehow something with boundary condition. And there are two conjectures which I want to finish my lecture. It's about kind of two different worlds. In the complex world, suppose I have a complex manifold, finite complex of homological bundles outside, or cyclic outside of compact subset. Then you can see the again this tubular neighborhood of a support of the homology. Choose any metrization. You don't need to use any Kahler metric. Kahler metrics were used only in Kahler identities before. So you use Hermitian metrics, arbitrary Hermitian metrics. You take this complex Laplacian depending on epsilon, and then the conjecture is the following: when epsilon goes to 0, you will get kind of spectral gap. Some eigenvalues will stay separated from 0, bigger than some constant, and few eigenvalues will be very close to 0, maybe exactly close to 0. And the number of small eigenvalues when epsilon goes to 0 will be the same as dimension of R gamma of my variety of open neighborhood with this coefficient, this complex of vector bundles. So the intuition is here is the following, because when we consider this Laplacian, one can see that its Laplacian is kind of very, very positive, get something epsilon minus square by square of norm delta outside of support of cohomology. And this eigenfunction should be some kind of smooth function, but like supported in a very, very small neighborhood of expected this support set. And so the details how we put Dirichlet boundary conditions far away will be kind of irrelevant. You get exponentially small corrections. Yeah, so that's a conjecture. So you get small eigenvalues correspond exactly to this. We'll have maybe a symplectic extension epsilon, and will be identified with global cohomology. And kind of first calculation indicate that if you apply it to our situation, then my bundle is actually bundle of forms, and this is multiplication by df. You get something interesting. You on this cohomology, or whatever this stuff, which is more or less identified with standard space, you have kind of harmonic representative depending on epsilon, and epsilon goes. So it means that you get certain L2 norm on this cohomology depending on epsilon, and when epsilon goes to 0, this norm will grow like different powers of epsilon in different parts of the subspace. So definitely should define certain filtration by some real numbers, and this seems to be essentially the same spectra which we are looking for. Or it's already non-trivial for isolated singularities. So it will be kind of geometric definition of the spectrum, not a formal one using some machinery of Hodge structures as in Washington single theory. But there is also a real conjecture, and as I told you, that's only one of these conjectures. The real one is important to the proof this non-abstractness. One can forget this about complex one. And that's the following. Now we start with real manifold, and with the remaining metric, and with a real function which is with a compact critical locus. And again, we can assume that only critical value is 0, maybe locus is connected. Also, I can add some piece of data which wasn't really used here, local system on my manifold, could be not unitary one. So the conjecture is the following one. Let's consider operator acting on forms. Again, use some nice neighborhood. which is d plus rescaled multiplication by dg, and take anti-commutator of the separator with itself. That's a famous Witten deformation of the RAM differentials, conjugation by exponent of function divided by e epsilon. And when he discusses in the case when manifold is compact and function has most critical points, then the statement was that for this deformed Laplacian, there was a part of spectrum which separated from zero, and part of spectrum which very close to zero. It will be spectral gap between them, and part of spectrum close to zero has dimension equal to the number of most critical points, and critical values are exponentially small. And here, using this Dirichlet boundary condition, one can assume that's not compact manifold, but took a neighborhood of critical locus. And then the conjecture that even without its Morse singularity, not Morse singularity, this close to zero eigen vectors should form a basis of homological pair, which nature associated to the situation when I get compact critical locus. And if you have local system, you can put local system as a coefficients. Yeah, so it's pretty interesting conjecture. I don't know whether people studied it. And if it's, again, sample calculation indicates that it should be true. And if it's true, then we will have unabstractness as our situation. We can finish. Thank you.
Thank you. Questions?
Okay, so the question is, if you deform this G into a Morse function, yeah, like trying to reduce to the Witten case. Yeah, and
you mean in real case?
Hold on, you have only semi-continuity, all right? But if you consider expansion in epsilon, if you're interested in formal series as he did, can you?
Sorry, I am speaking about real situation or complex situation?
Real, the last one.
The last one, okay, yeah.
Yeah. I mean, it just because if G is Morse, it's exactly Witten's story.
Yes, yes.
Compactness is not essential.
Yeah.
But if you're interested in formal series and epsilon only, can you reduce the question to the Morse case by deforming G? Because it's a question about kind of a real.
It's not clear to me at all, I have to say. I don't know.
No, I don't. Okay.
I don't.
It's not clear.
Not clear.
Not clear. No.
Okay.
Other questions? Ezra?
Yeah, hi.
Hi.
So in the complex case mainly, so I just was wondering if it might make sense, instead of using something like Dirichlet boundary conditions, to instead use Homunder's approach of essentially introducing a volume form, which is the exponential of a strictly pseudo-convex function.
Maybe, yeah. I think those details are really irrelevant. This is because eigenvalues will be concentrated so close to critical locus.
Yeah,
it should be relevant, yeah, but I don't know in what sense.
Okay.
If not, let's thank Max again.